So topic of today's lecture is effect of scale and physical properties on hydrodynamics. So something we will repeat again that we have already discussed with Professor Angeli in the last class, and then we will see few effect of how you change the physical property and what is the effect of changing the physical properties of the continuous phase on the hydrodynamics. So let us begin with again the basic definition of two-phase flow. So we know two-phase flow is a kind of interacting flow of either two phases or two components. Okay, so pause कर दिया आपने? मेरे उसमें भी है. उधर ले आओ. इसमें पीपीटी करके एक फोल्डर है, उसमें फाइनल करके फोल्डर है, उसमें लेक्चर 3 पीपीटी फाइनल लेक्चर 3. Okay, so let us continue. So we can have different types of two-phase flow. So when we are discussing about two-phase flow can be gas liquid, that is widely researched. Then it can be liquid, it can be gas solid, it can be liquid solid. Okay, so the examples of application in industry are listed over here. So what I presume in this class, we have a mix of chemical engineers and mechanical engineers, right? So chemical engineers, we can think of gas liquid application in conventional channels. Okay, so we have lots of industrial application. For example, in refinery, we used to do an operation called desulfurization of flue gases. Okay, so you want to remove, let's say, sulfur dioxide from the flue gas. So what the operation you can think of? It is the absorption column that we can have, and in the absorption column, the sulfur dioxide from the gaseous phase can be absorbed in liquid phase. So when it is getting absorbed in the liquid phase, of course, this is a gas liquid operation, counter current gas liquid flow, and at that top of it, you have mass transfer, sometime also accompanied by reaction. So in industry, what we are seeing, not only two-phase flow, but rather a complex form of two-phase flow where it is accompanied by mass or heat transfer or reaction. Similarly, again, petroleum industry, what we can think of, another example is given. So petroleum industry, when we are doing for oil exploration, so it is not only the crude oil that is coming out from the well. It is a mixture of oil, natural gas, and sometime with the sand particles. So in fact, it's a three-phase flow. And if you inject, if the oil is getting depleted, sometime we inject steam, okay, in order to extract more oil. So it is a mixture of at least two phases. There is steam coming out, and you have uh, oil, crude oil. So there are n number of example we can think of for liquid two-phase flow or gas liquid two-phase flow. Okay, chemical engineer, another example in industry is extraction, where the liquid flow is accompanied by again mass transfer. Again, for example, for mechanical engineers, okay, you can readily correlate like the phenomena like boiling, condensation, and their application in power plant and in refrigeration cycles. Okay, so we have plenty of application both for liquid and gas liquid flows, and similarly for gas solid and liquid solid flows. Okay, so this is kind of overall picture of two-phase flow in industry. But we have ample example in our daily life also. We are surrounded by two-phase flow in our daily life. So the simple phenomena like fog or rain is a kind of interaction of two-phase flows. Ocean waves, again, example of two-phase flow, two-phase interaction. Okay, so when you are maybe if you use a bathtub, if you fill it with water and suddenly you try to open the opening from the bottom, so while you are draining the bathtub, there is a sound, there is a hissing sound. Why the sound is happening? The sound is happening because there is a vortex formation, there is a air water interaction that is happening at the bathtub draining pipe. Similar thing happen in the kitchen sink also. Okay, so in day-to-day life, we are also surrounded by this two-phase flow examples. Now, this till now, I haven't classified typically what is macro and what is mini channel or what is a micro channel. So, these are the example uh, from the industry as well as daily life. Now, when we are talking about general two-phase flow, it can be maybe can classified. Last example that I have given for chemical and mechanical. So chemical people may be more correlated with, let's say, absorption, power or extraction, right? Where you don't have any change of phase. Okay, but yes, one species, one component is getting transferred from one phase to other. While mechanical engineers, while you are doing the power plant engineering, etc., and refrigerations, so in that case, you may be encountered with something when a single phase is being introduced in the test section or uh, any pipe for that matter, and during flow it changes its phase from liquid only to a mixture of gas liquid and finally only gas or only vapor. Similarly, so you widely we can classify two-phase flow with categories: flow without phase change and flow with phase change. Okay, flow without phase change with the examples of like mostly like liquid flows where we are not changing the phase, or any gas liquid operation, air or water operation where we the phases of the flow are not changing. While for example, if we operate in a nuclear power plant or any power plant for that matter, where you can producing steam from water. So this is not something that is happen at single go. There is a continuous change of phases of the liquid. Gradually the liquid changes to the vapor or steam. So this transition, when it takes place inside the tube, you observe two-phase flow phenomena. Some example, some simulation we have done on vapor liquid flow. So this is this is the example how dynamic change can take place in a phase change uh, phenomena when it is happening inside a tube. So for example, in this particular case, we have tried to simulate the vapor and liquid flow configuration. We started with an annular distribution, so you can have vapor inside and liquid outside. So what happened? We have certain degree of superheat at wall and the liquid is saturated so as the vapor. So when the flow progresses, gradually we could see some disturbance wave at the interface and certain nucleation site at the wall because the wall is heated. So you could see some vapor bubbles are generating underneath this liquid film. So this is axisymmetric interpretation. So, some vapor bubbles are generating under the liquid film, as well as the liquid film is also not stable. That is some kind of shearing action it is facing, and gradually some disturbing wave is being generated, and gradually some pinch of the drop happens. So this is the drop, and this is the vapor bubble that is growing adjacent to the pipe wall, and ultimately it is the snapping of the liquid film occurs and the wall is getting directly exposed to the heat. Okay, so so such phenomena with phase change is much more complicated and much more interesting to see. Okay, so what I'm trying to give you an through examples is that what we study liquid with all various assumption, the two-phase flow, and what the industry is actually doing is far more complicated. We have a simplified form where we are trying to figure out what is the geometric distribution, what is going to be the pressure drop. But when the flow is accompanied by any other transport process or any phase change, so the matter is really interesting as well as complicated to study. So all these flow patterns can be again well classified under two categories: well separated and well mixed. So well separated is the flow pattern where your interface is very clearly you can see. So example are annular stratified distribution where you can track the interface very clearly. Well mixed is where the one phase inertia is driving the other phase. Okay, so the secondary phase is completely dispersed in the primary phase. So example is any kind of dispersion, bubbly flow. So, and from the last class I gather maybe there is some recapitulation probably needed from our tutorial, that we have, in the tutorial we have similar type of setup, right? So what we are noting down in the tutorial, we are noting down the volumetric flow rate, right? In terms of what? What is the unit? Millimeter per hour, right? ml per hour. Okay. So now if in the tutorial the last question is being asked to you is to draw a flow pattern map in terms of superficial velocity. So what is the superficial velocity? How you can calculate superficial velocity is, once you know the flow rate and the pipe diameter, you just divide it. Okay, so this is the gas, you can say volumetric flux or superficial velocity. For the liquid is the liquid volumetric flow rate divided by the entire cross sectional area. This is called the superficial velocity of the liquid. When you sum it up, this is the mixture velocity. Okay, now so probably now we can draw the flow pattern map from today last class last tutorial example, right? And there is another basic information is that this quantities beta is inlet volume fraction. Okay, inlet volume fraction is how much of one phase is being injected in the test section. So this is, let's say we want to calculate from the last tutorial, we want to calculate the volumetric flow rate of, let's say, toluene, our dispersed phase in the tutorial. So this is the volumetric flow rate of the toluene divided by the total volumetric flow rate that we have injected. That gives you the value of beta, that is inlet fraction. Okay, similarly, if you both the phases are incompressible, so you can multiply the densities, corresponding densities, and you can get the mass flow rate of the phases. Now there is another volume fraction that is very interesting information can be gathered from this volume fraction, that is in situ volume fraction. What is in situ volume fraction is that, suppose this is the cross sectional view, okay, of any flow distribution. Let us assume that the slug flow that we have observed yesterday. So if you, in the slug, if you want to have this kind of cross sectional drawing, then probably this white space is occupied by toluene and the rest of the space, the gray space, is occupied by water. So this total area is the tube area, that is the cross sectional area of the tube. Partially it is occupied by phase 1 and partially by phase 2. So when you divide the actual area occupied by the phase inside the tube uh, volumetric flow rate by that actual area, so that gives you the in situ velocity. Okay, that is the actual velocity with which the phase is actually traveling inside the pipe. Okay, so that for that matter, alpha is what we are saying about alpha, alpha is a ratio of the areas occupied by, let's say, this dispersed phase by the total cross-sectional area of the pipe. Okay. Yes. So it is area average volume fraction. It is giving you the ratio, okay, of areas.
Then by default it assumes the neglecting the and effect on both sides, whatever volume you are.
See, what we can give the idea or estimate about the ratios of the phases inside. We can have three different type of information. One is how much length of the dispersed phase is occupying over a total length. Second is how much area of the secondary phase is occupying by the inside the of the total cross sectional area of the tube. Third is the how much volume is occupied by the dispersed phase in a particular volume. So any ratio for that matter giving you the idea that how area of the secondary the ratio of the dispersed phase is occupied inside the tube. Okay. Third is the how much volume is occupied by the no. Yes, if it is properly dispersed. So dispersed phase, when I say it is the secondary phase. Okay. Secondary phase, let's say for example, the toluene that we have taken, that is not dispersed in the sense, but it is kind of a secondary phase which is forming the flux inside the tube. Right. So that is what, that is the terminology used for the secondary phase. So obviously when it is completely dispersed, then the beta and alpha are secondary phase. Let's say for example, the toluene that we have taken, that is not dispersed in the sense, but it is kind of a secondary phase which is forming the flux inside the tube. Right. So that is what, that is the terminology used. No, we have different, see, flow pattern based models are different for different things. So we have separated flow, we have reflux model, we have homogeneous models. So separated flow models are developed based on the fact that that annular or stratified kind of flow regime can be modeled. So pressure drop modeling or modeling of any sort is dependent on what type of flow pattern you have. Okay, so this is kind of a general idea that we are giving, that what is alpha, regular notation used in two-phase flows. In situ volume fraction can be measured through various probes, using various probes. Okay, if you have some, for example, conductivity probe, if you have optical probe, okay, or if you have some other technique which can somehow measure what is the length of occupied or what is the area occupied for a particular cross section by one phase, then it can be possible. Okay. So this is some example giving the how the physical properties are affecting in macro channel. Okay, so what happened if you change the physical property in macro channel? Some quick example before we move on to our main discussion. So these are the example where you have where the experiment is carried out with two liquids rather. The first pair is lube oil and water. This is this one, and the second is kerosene and water. So the densities of both the phases are close by. However, the viscosity of the lube oil is very high in comparison to kerosene. And here it is surface tension that is given. Okay, so surface tension is also different from the kerosene one. So as a result of which, what we have seen during the experiment, that the pattern of so both in these two cases at the same superficial velocities, they are forming annular flow. Okay, this is a vertical experiment. Okay, this is a vertical experiment. So we have seen formation of annular flow in both the cases, but you can certainly see the distribution, though it is annular, the distribution is not the same. Okay, so it is the pattern here, it's kind of asymmetric in nature, and this type of wave that is generated at the interface is called bamboo wave. Whether in case of kerosene, so you can see the wave pattern is different, and kind of this kind of distribution with very difference of phase velocities, these are superficial velocity, in situ velocities are widely different, so give rise to some kind of instability. And as a result of this instabilities, what happened, this wave, disturbing wave that is present in the interface, they grow in magnitude, and from both ends they touch each other, so they are breaking this core. Okay, while it remains so distorted but continuous. However, this has been already snapped. Okay, so this is the effect of if you change the viscosity, if the if you are doing the experiment with a high viscous dispersed phase, high secondary phase, then what you can expect. Similarly, yes, and this one is the effect, viscosity and the interfacial tension. So effect of interfacial tension can be seen over here, that when you have much lower, kerosene has much lower interfacial tension. Okay, kerosene water interfacial tension is much lower than the interfacial tension of lube oil and water. So what happened here, we have observed dispersed flow, but that is not observed in this case. Okay, so both the effect of viscosity and the interfacial tension are there in macro geometries. Okay, now let us move to what is the course is all about, is the miniaturization. So first of all, why the miniature reactors? So this is already, I guess, known to you. They are for high surface to volume ratio, safe environment of operation, and they enhance mass transfer, any transfer process for that matter, and that is why they are used as a tool of process intensification. Okay, so we are moving now to the miniature reactors. So this is some example of the real life reactors and some examples of how things are carried out in the miniature devices. So this is an example of gas liquid reactor that we have used in our study. This is also the same. So this is just a single line, and this is multiple serpentine channels. Okay, this is for the liquid-liquid distribution that is obtained in case of a miniature tube. Okay, so this is what we call. This is actually, if you look here, it is a plug, inside that a drop. Okay, so effectively it's a three-phase flow. It's forming an encapsulation of a liquid inside a liquid. So such kind of encapsulation can be very effective for encapsulation of any vitamin, encapsulation of any drug, which can be delivered later. So such kind of distribution can have lots of application in pharmaceutical, cosmetic industry, etc., and food industry. Okay, so now let us define what we have, what is the classification. So I gathered that already you know, but there is two type of classification based on the ratio of your buoyancy or to the surface force, as well as based on another definition is provided just based on the channel diameter, whether the channel diameter, if it is higher than 3 mm, so we call it conventional one, mini lies within 0.2 mm to 3 mm, and micro is 0.02 to 0.2 mm. Okay, so now let us see. So this is almost the same thing that we have discussed till now. But what to expect? So surely the forces are different in many channels. So the main question is that whether the distribution that till now we have discussed, okay, and we have seen they're getting affected by so many things. They are in macro channel, they are getting affected by orientation, physical properties, volumetric flow rate combination. Okay, so the question is whether the information that already we have, okay, in the literature for gas liquid or liquid liquid about the distribution, can we apply the same knowledge in the mini, or we need some additional information? So for that, this is some kind of, again, I just gathered that Professor Angeli already has shown this non-dimensional numbers to you in the last class yesterday. But again, just recapitulation. So the ratio of the forces in the miniature geometries are widely different for that that exists in the macro channel. Okay, so some of the important numbers are listed over here that we use frequently for reporting, for analyzing the flow regimes as well as pressure drop in case of miniature geometries. So we started with Reynolds, then Bond, capillary, Weber, Onsurge. So this is the typical flow pattern, flow distribution in gas liquid miniature geometries that is being reported. So you could so okay, bubbly we have seen, slug we have seen, and annular also we know, churn we know, annular again we understand. Mist is one of the flow regime. What is Dr. Garg and myself, we are discussing about the mist. So this is the mist kind of distribution. So this dots now are of liquid, and the continuous is the gaseous phase. Okay, and another interesting phenomena that is being reported is the liquid ring formation. So here you have a continuous gas core, and sometime what happened due to liquid accumulation inside the mini channel, what you can see is kind of a ring formation. Okay, so in a 3-dimension, it is 2-dimensional representation is not very clear. In case of a 3-dimensional observation, you could see is a liquid ring enclosing the gas core. Okay, so this occurrence, okay, annular, you can say the interface is more or less steady. There is no, this film is somehow there is a drop over here, the interface is disturbed. But here from both the side, the interface is kind of getting the some kind of accumulation or disturbance on its flow path and forming something like a clamp. Okay, on the annular, it can be a mild disturbance on the interface, but that is not forming the liquid ring. Okay, I have some pictures of the liquid ring flow. Maybe I will try to show in the next presentation. It will be more clear. Okay, so
gas phase is close to the annular region, but the liquid phase that is flowing.
no. So it is the liquid one that is adhered to the wall, and basically what happens, the liquid film is very thin. Okay, and on the thin film, when the liquid accumulates at certain point, then it is forming kind of a ring structure. From both the side there is a accumulation, so it is forming kind of a ring structure on the gas core. Okay, it is compressing the gas core at a certain points. Okay, so certain points you can see some kind of compression along the core. So that is a liquid ring formation. So it is different from the annular structure. They are to certain extent may be similar, but the distance in the annular is different than the ring.
Let us show the molecular for the liquid that is clear.
Okay,
Liquid is in this.
I will show you in the real pictures in the next class. Okay, so figure out this confusion. Now, so Mishima and Hibiki they have very nice experiment they have done on the entire regime of from 5 mm tube diameter to 1 mm, so that they could gather the what is the actual difference when you are gradually progressing towards the mini channel from conventional channel. So this from here you could see. So this orange is definitely the air bubble. So here bubbly flow is what you can gather, that okay, they are finely dispersed bubble, okay, uniformly present throughout the tube. While when you are narrowing down the flow path, okay, so they are closer to the axis, okay, the diameter is slightly enlarged. Sometimes they are also forming kind of a train, okay, one another, something like that. That is also we have observed during the tutorial yesterday, isn't it? A train of bubble, okay, a train of small plugs, one by one they're forming. Similarly, what happened in the slug? So slug also this type of thing we have seen, okay, a slug followed by small drops, okay, so small drops in the liquid bridge. Okay, so from the tail of this of this, you know, this one, so some drops are detached and forming that kind of dotted droplets over here. So, and they are gradually becoming longer. So if you recall, in the last tutorial, when we are moving from 2 mm to 1 mm, we have seen such kind of long plugs, okay, at the dissection. So this is the effect of narrowing down. This is the effect of increase of surface forces. And the churn, this is for 5 mm, this is for 1 mm. So churn is basically, you could gather that it's a very unstable regime in macro. However, the form changes in case of miniature geometries. Similarly, we have some representation for this kind of liquid one. Okay, so the liquid one, again, what we have seen from our experiment also, from different phase velocities, different types of liquid flows, that it is what we could say droplet disperse, not entirely disperse. In dispersion also sometimes we see, because two small drops can join that, and sometimes we can see larger drop. Okay, so that is called droplet dispersed flow. There's a mixture kind of a flow, okay, mix of droplet and finely droplet. Actually, the distribution of droplet size, you can say. Then this is very interesting one. This is parallel flow. Uh, this parallel flow is kind of when you have a special type of inlet where two fluid may be injected. Let me see if I have this one. Yes. Okay, so something like this kind of a injection pattern that can give rise to that parallel flow. Okay, so they are getting introduced like this with higher velocity of this particular phase, this liquid phase. So they are getting forming a long jet, okay, over the channel, and with so that is we call jetting. And further increase in this particular phase, their two fluid are flowing simultaneously, having some kind of parallel distribution, co-flowing. Uh, why I'm not using the term stratified deliberately is for the stratified flow is very correlated with macro geometries, and the stratified flow is basically formed due to the interaction, stratification due to buoyancy forces. Okay, so it's a stratification due to densities, right? So the lighter density occupied the top one and the lower density, definitely. This one is not kind of that you may change the inlet, you may not get the parallel flow. Okay, so that is why I deliberately not using the term stratification. Okay. And some other, so this is about jetting that I'm talking about. So it's a long jet formation and then it is getting snapped. Okay. So these are some typical representation of liquid-liquid flows. And this is again, I guess we have enough discussion in the last class tomorrow regarding the mismatch that we are getting for the flow regime and various transition predicted. Okay. So the basic idea is, okay, this is not a good match when we are try to use our knowledge from the macro channels, and then we are trying to match the transition geometries for miniature one. They are not fitting, indicating again or emphasizing the idea that the forces used for formation, or the forces that are responsible for formation of the flow patterns in the miniature geometries are different from that of the macro geometries. So this is typically when we have done, this is the typical flow regimes that one could expect in a macro dimension. Okay, so in macro dimension, horizontal orientation, you bound to get stratified or stratified smooth. Okay, dispersion in case of you are using liquid-liquid. And one more interesting phenomena that happens in macro for liquid-liquid flows, that is phase inversion. So when you are seeing that this type of dispersion, and suddenly with a small change in the geometries, in the operating parameters, it may land up with this type of dispersion that is called phase inversion. So, and in case of the vertical orientation, we are mostly getting annular distribution, while stratification is absolutely not observed in macro channel. Okay, for vertical orientation. So what is the difference that we are getting when we are moving to miniature geometries? So this is some summary that we have done the experiment in the miniature geometries with different confinement number, and we have seen that effect of orientation when we gradually, so we have performed the experiment with let's say 1.65 mm of hydraulic diameter, 1 mm of hydraulic diameter, and 0.65 of hydraulic diameter with a confinement number corresponding to 1.6, 2.2, and 4, and the fluid are air and water. So what we have seen, as the gradually the confinement number is increasing, so there is, when you plot the flow pattern, the range of existence are similar for horizontal and vertical. So I'm not saying there is no effect of orientation, but gradually when you are moving or increasing the confinement number, the orientation effect is disappearing. Okay. Then existence of, majorly when you move to 0.65, there is majorly, it is inertia driven annular flow that we have seen in both the cases, both the orientation. Okay, so factors that are affecting the mini and micro, in summary, what we could say, the factors affecting mini and micro are not the same. Okay, so what we observe that the inertia is responsible for formation of annular flow. Slug and stratified, or not stratification, you can say mostly is the slug is resulted from the viscous and interfacial tension, and the droplet regime is governed by mostly shear forces. Okay. All right. So now, till now, we have just discussed about the scale effect, right? Now let us discuss about if I change the physical properties in miniature geometries, okay, so what I could expect. So again, this is the experimental setup. So this is the straight tube of glass. This is a glass capillary, similar thing that we have already seen. So this is light source, camera, okay, pressure transmitter that we haven't seen last class. So this is pump for both the phase is toluene and water. So here what we have done is that we have kept the toluene as it is, but gradually, so first one we have performed with toluene and water, second one toluene and distilled water mixed with 20% of glycerol. So what does it change? It changes the density. Okay, though the density is close by, it changes viscosity as well as changes interfacial tension. Okay. Further we add 40%. So again, the density changes, viscosity become more viscous and interfacial tension goes down. So we have now 4 pairs. First this one, second this one, third this one, and fourth this one. So this is the result, okay, at particular superficial velocity, okay, at a particular volumetric flow rate combination for both the cases. So the volumetric flow rate remains same for this case, this case, this case, and this case. Okay. So if it is the toluene is 2 ml per hour and water is, let's say, 1 ml per hour, that remain constant for all the other cases. So what we have seen that, so what phase physical property is changing? Which phase we are changing? Continuous phase. So the continuous phase is actually getting more viscous. Okay. And the interfacial tension between the phases is reduced. So what will be the effect of it? The slug length is gradually reducing. Okay, since we have changed, we have reduced the interfacial tension, it is easier to form the slug. Okay. At the same time, since we have increased the viscosity of the continuous phase, it is also kind of exerting more interfacial shear. The viscous force on the disperse phase is higher. So as a result of this two change of forces, it is what you could see, small, well-defined slugs are formed, okay, with the same flow rate combination with the 60% glycerol.
Soluble.
No. They are immiscible, that is been tested. So this is the flow pattern map for all the cases. So in order to have, since we have difference of physical properties exist in the phases, with phases having different density, viscosity, and surface tension, that is why they have plotted in terms of non-dimensional numbers so that we can have a more better idea about the forces that are acting on the phases throughout, so we can compare. So what you could gather over here, that in all cases we are getting the slug, that is very true, but the slug characteristics are different. Okay, so this is the result I want to show and to share. And further, how it is affecting. So you have seen that there is a pressure transmitter. So the differential pressure drop is being reported over here. So here, what is the observation? So as the continuous phase is becoming more and more viscous, and it is expected to rise the pressure drop. So the pressure drop is being increased, okay, few fold. Maybe the highest pressure drop, if you could compare, it is at least more than 2 times for the more viscous or the least viscous and the highest viscous continuous phase. Okay, now So first, so this is a simulation that we have done recently, the VOF. So it is giving you the ratio of the dispersed phase by the continuous phase, and we are gradually reducing the viscosity ratio of the dispersed phase Okay, so we are gradually reducing the viscosity of, you can say either we are reducing the viscosity of the dispersed phase or we are gradually increasing the viscosity of the continuous phase. So ratio is decreasing. Okay, and you could see it gives us the similar result that we have obtained in our experimental observation about the slug size. So slug is getting more and more change of length. You can observe shape also can be quite different from what we observe over here. Okay, so I gather we have few minutes. I don't know whether I'm able to complete. Meanwhile, do you have any questions for till this much? Okay, so in the last lecture, Professor Angeli discussed quite a lot about the pressure drop. Okay, and she has shown a different correlation that exists, the useful correlation that exists for miniature geometries. Now, so maybe at this point we need some recapitulation of what is the existing pressure drop models that are there for macro geometry. So one such widely used model is homogeneous model. So homogeneous model assume there is no slip between the phases. Both the phases are mixed, is well mixed, and it is acting like a pseudo fluid. Okay, with some mixture properties. So what are these mixture properties and how they are estimated? So in this case, they are estimated with inlet volume fraction. Here we assume alpha is equal to beta. So the estimation of mixture properties, or this is the most advantage of the major advantage of homogeneous flow, that you can estimate the mixture properties using the inlet volume fraction. Okay, you don't need the in situ volume fraction or in situ information for that. So there are two ways to estimate. So if you have both phases flowing without any phase change, you can go for this. You can go for this. But if you have gas, let's say vapor liquid flow, where the phases are being you started with liquid, and gradually as you move you are encountering the formation of vapor phase. So maybe in such a situation you need another factor, that is, this is the mass fraction of what we call, this is, so this is the ratio of the vapor to this is mass ratio of the vapor to the total mass that is being injected. Okay, so on basis of these two parameters it can be estimated. So you can either use this one or use this one. So if you have a change of phase that is occurring inside the tube, we will definitely go for this correlation for estimation of the density, and this is for the viscosity. Okay, so once you have estimated the properties, then you have the component of pressure drop. Okay, they are responsible for the total pressure drop that is you are recording. So one can be friction, one can be gravity, one can be acceleration. Now the friction is, it can be estimated very easily. Now let us first, because in majority of the cases we are very interested in the frictional pressure drop. So the frictional pressure drop, so this is what is Fm is the, so this is the subscript M stands for, it is for used for two-phase flow, okay, two-phase flow friction factor. But how to calculate it? Okay, so how to calculate? Obviously, it is what we have started with is a pseudo fluid with mixture properties. Okay, so we are saying it is a fluid with some change properties. So for that, how can you estimate friction factor? First, we are going by the same correlation that we are using for the macro, but here the Reynolds number estimation is based on the mixture velocity and the mixture properties. That is the difference. Okay, gravity again rho mg sin theta. What about the acceleration? Now acceleration has two components. One is this one, that dA by dz. If you have a tube geometry which is changing along, if its area is changing, okay, along the length, then this component gives rise to some amount of change in pressure. As well as if you have a vapor liquid flow where your mass fraction, okay, is changing, because it is continuously, you are from the liquid the vapor is being produced, so the value of x is being changed. So for that also, if it is, you can have certain amount of change in pressure that is accounted. So the acceleration pressure drop is made up of these two different components. So in most of the cases, if you are dealing with no change of pressure, no change of phases and a straight tube, then probably this equation becomes simpler. Okay, and further you have friction and gravity only to calculate, and mostly it is the frictional one that we are estimated. So this model is being developed for macro geometries, working perfectly fine for geometries, for bubbly, for dispersed flow in macro geometries. But is it working fine for miniature geometries also? So this we have checked and we have observed, no, it is no. So you can see the error we could get with the experimental pressure drop. We could get over 50% of error with the homogeneous one using try to model dispersed flow, okay, droplet dispersed flow. So this is the kind of error we encountered. Then what we have tried a bit to modify the friction factor. Now it's we tried to figure out if we could give it in terms of Weber and capillary. Of course, similar correlation are reported for air water in miniature geometries. So we have figured out, so it is not is a function of Reynolds, but if it is a function of, you know, something of more, whether the surface tension is coming to the picture, interfacial tension is coming to the picture. So in that way, we have taken into account the Weber number. Okay, and it is more or less fitted with the experimental observation. Okay.
Empirical, or here you give it the dimensional error?
No, it is empirical one. This one we have from the, we have lots of experimental data. We have tried the fitting. Okay, for different values of C and N are observed for different flow regime. Okay, so with this, I want to conclude today's lecture. Okay, have any specific question? Okay. So we will continue after the